All right, so with this question, F2 on page 26, again, similar to the lab in terms of big ideas. We've got a new toy that consists of a car, mass M, on a nearly frictionless bearing and in a spring-loaded launcher. Now, the question is, what does nearly mean? Do we still take into account? No, it's frictionless. Just go with that, okay? And so I'm just going to cross that out. We'll consider it frictionless. An apparatus that's not shown within the launcher to compress the spring any distance and then release the spring so that the spring transfers all of its energy to the car. A student is given this toy and asked to make a hypothesis about the relationship between the spring's compression and the subsequent motion of the car. Here we go. The student hypothesizes that if the car is launched horizontally, the launch speed of the car is directly proportional to the compression distance x of the spring. Well, first of all, we need to know what directly proportional means. It actually means two things. What do y'all know about directly proportional? If any two terms are directly proportional, it means, say it louder. It's a straight linear line. So your graph would be a straight linear, constant slope, right? Constant slope. And it means one other thing. If one variable increases, the other increases. But even closer to that, if one doubles, the other term doubles. Now that wasn't the second thing I was going for, so maybe we had a third. And so if you double the x variable, then you double the y variable. Okay, so that's a true statement. The other thing, it passes through the origin. Okay. And so anytime you see directly proportional, this is what it should mean. So we've got to prove or disprove this student's claim that X and V are directly proportional. And we got to remember what directly proportional means, okay? And note to self, in free response, when you are writing stuff about graphs, if you say the words directly proportional, the grader is going to assume you're indicating these three things, okay? And so if the question is not directly proportional, but you say it is, then you may not get full points, okay? You can still have an increase. You can still have a trend that doesn't go through the origin. But if that's true, you won't have a double or triple. Okay, it all starts with an equation. And so we compress this spring, we store what kind of energy? Potential elastic. And so we're starting out at full compression with an elastic potential energy. And so, by the way, since they said it's frictionless and there's no height change, we're just going to take a, conservation approach. And so in the beginning at full compression, we only have elastic potential energy. Now let the spring stretch out. Says all this energy is going to transfer to the car. It's all going to get converted to what kind of energy? Say it louder. Kinetic. And that is our conservation statement. No frictional losses, no height change, so there's no gravitation. This is it. And so we want to put it in terms of V and X. And so elastic potential energy, 1/2 K X squared. Now, personally, I like delta X for the compression, but since they've already identified, you want to make sure you use their terms. Okay, it's part of playing that AP game. Okay, if they define compression distance as X, make sure you use exactly X. And then kinetic energy, 1/2 mv squared. So there's the V that we're interested in. And what do they say It says the equation will probably contain some constant quantities. What's constant in this setup? Mass and the spring constant, right? At least constant for the moment. 1/2 and 1/2. Hey, look, what could you do? You could cancel. You don't have to, but you could. 1/2, multiply both sides by 2, and it goes away. And so, use the equation to evaluate the student's hypothesis. And so they talked about X and V proposing direct proportion. Are they right or are they wrong? They're right, because what happens if, so student is correct. If you double the compression, what's going to happen to the velocity? Well, notice both X and V are both squared, right? And so if you double the compression, then X squared is going to be proportional to 4. Which means 4 will be equal or proportional to V squared. And so what would V do? It would double. And so that double, they're both squared. When would it not be proportional? Well, what if only one was squared, right? Okay. Now, part 2, it's not every time that you have to write out a procedure. Today, in the real lab, you're not going to have to write out a procedure, and it is going to vary a little bit from this one, but the physics that we just did is still true. And so, outline a procedure whereby the student could use commonly available equipment, so we're talking stopwatch, rulers, the common equipment, to make measurements in order to test the hypothesis. And again, they propose that it's directly related. Draw and label the diagram of the experimental setup. And so, by the way, they're not grading your artistic value, just you want to label the physics, focus on the physics here. And so, what would we use? What equipment would we use to measure what? I already told you too. Measuring tape or ruler, right? So some kind of measuring device. I'm going to say ruler, there's less to write. Meter stick, measuring tape, ruler. What are we using it for to measure? What are we going to measure with this ruler or measuring tape? Initial position. And so we're fully compressed and we make that measurement. And remember, they want compression distance or delta X. And so to get delta X, we also need a final position. And if you're like, but it's 0, okay, but something's got to be said about that. It could be 0, it may not be. Today, when you make measurements, maybe 0's on the floor and you have 2 other locations to measure. And so both of these are going to help you get, and so this will help you calculate this compression distance. And they talk about drawing labels and setup. And so earlier, they showed us that glass tube and maybe there's a spring in there. And so this might be your initial. And then final, we compress it and we put that car inside. Good deal? What else? Stopwatch. What would the stopwatch be useful for? It doesn't record velocity, time. And so a stopwatch or timer would measure time. Now we are going to use time to get a velocity or speed, but we need one other piece first. What do we need to get speed? Distance. So maybe we get that ruler back out to measure a distance. And then together we can do velocity equals distance over time. Now, what distance? Is it going to equal the compression? Probably not, because maybe if you're inside a glass tube, I don't know if we can see inside, right? And so maybe there's some distance outside of the tube that it travels, and you'll get the time for that. And the reason I address that, it's frictionless. And so the average velocity would equal a constant velocity. Because remember, d over t is really an average velocity. Everybody good there? Okay. Anything else to measure that might be needed? I forgot this in the last class, but we still have mass involved. It didn't cancel out. Shouldn't we measure the mass so we can continue? And so how do we measure mass as something? A scale. And so a scale to measure mass. And I don't think you really have to draw that scale out. I mean, if you had time, you could, I guess, but those can vary. Good deal? Oh, and what's another good thing a good scientist does when they collect data? You make these measurements. Are you perfect the first and only time? No. So, and we're using a stopwatch here, at least in our setup. And so we're not going to get that perfect timing. So what should a good scientist do? Multiple trials to reduce error, right? To reduce random error. Okay. Everybody good with part 2? Part 3 says, explain the process of data analysis. So we've collected data, okay? Maybe if you wanted to just visualize a data table, we have our XI, XF, we've got our time, our distance and velocity, mass. So we've got all this data. Now, what are we going to do with it to confirm or deny the student's hypothesis? How will the measurements be used to evaluate? We got to do something with linear, right? And so if we know directly proportional should be a linear graph that goes through the origin, well, let's see, what could you plot to help support this? So you kind of got to look back at our physics equation. We have kx squared, k is a constant, x squared is what the student is changing, equals m, which is a constant, and then v squared, which is what they're measuring. So what do you think we should plot on the graph? Y'all remember linearization? So that y equals mx plus b. Can we somehow get this in y equals mx plus b format? And you can go with independent, dependent variables. So what do you want to put on the y-axis? Velocity. So I can solve it for v. So it's a little reversed here, but divide both sides by m. And so there's my y equals. What's on your x-axis? The compression distance. And so let me do my highlighting here. So v squared lines up with y. X squared is going to line up with our mathematical x-axis. Careful, there's a physics X and a math X there. And what would your slope represent? And I'm going to write that out because I don't like doing M and M. So writing out slope, what would your slope represent? Not displacement. Spring constant divided by M would be your slope. And both of those are constants. And if you remember, you want to group your constants in that slope placeholder. Yes? Okay. And so if you plot on your graph v squared and x squared, then the slope should come out as a ratio of k to m. And y'all are going to do that today, okay? But you're going to use it to solve for k, not just prove a direct relationship. Now we know it's directly related, and y'all are going to do data collection. You're going to analyze your data and use a graph and linearize this graph if you, hopefully you know how now, and we're going to solve for k. Bless you. Good deal? After the lab, we'll finish this question because they're about to glue a felt pad on it and they're going to bring in friction. Our lab doesn't have friction. All right. Okay, so if you would go on and grab one of the lab handouts, there should be some in the middle of the table. If you need extra, you know, either come up to me or find an extra on a table. Okay. And let me insert the lab real quick. Uh-oh. Come on. Lab. Ah. So I'm putting it in OneNote just so I can write on it as we talk. Okay, so today's lab, by the way, due next class, so due Thursday. You won't get it all done in class today, but do is work efficiently with your small group, okay? You may have to do some of this analysis at home, and so hopefully you can get most of it done in class. I'm going to give you about 30, 40 minutes max. And so today we want to use a graph to solve for the spring constant. Now I'm going to go in and tell you right up front, there's a couple places in here. If you just do 5 separate calculations of k, because you'll have 5 sets of data, if you go, oh, k equals, k equals, k equals, k equals, and then average, you're not going to get any points, okay? That defeats the purpose of best practice, which is to do it with your graphing, okay, your linearization piece. And so we are going to collect some data. I've already set the stretch extension. Today, we're going to actually use rubber bands, just pretend it's a spring. It's elastic, right? It can still store elastic potential energy. And so the stretch extension of the rubber band, I've already preset those distances because I didn't want anyone, you know, stretching it for 2 meters. That could end in bad results. And so we're kind of Goldilocks in it. Okay, you'll start out with 6 centimeters, and then you'll work your way up to 18. So part of the data table already filled in, all right? And then for velocity, and so let me walk over here to the setup. You've got a fixed end, okay? And the rubber band should be attached so that it doesn't slip off, but you've got a fixed end, and then the rubber band kind of lays on the track. You want to find the happy place of your system. What do we call this happy place? Where it's not stretched or compressed. Equilibrium, okay? And everyone is going to have slightly different, but you'll make note of it. So maybe this one's, you know, 74, 79. Eyeball. Be careful in your measurement. And then we'll stretch it 6 or whatever meters, the centimeters. And then before I let go, someone is going to come over here to our lap pros. Hold on. Right, someone's going to come over to the lap pros and hit the green triangle. So this isn't on the screen right now, but the green triangle, if you listen carefully, it doesn't sound exactly like that, but it starts clicking very quickly. That means it's collecting data. Do we want our hands in the way of the detector during data collection? No. We want hands away. So that person holding it in place, be on the other side of the car. Okay, when you lift up, move your hand back. And then when it starts going into the rubber band, you can stop it. Okay? You don't want it to crash into that fixed point. Okay, these little silver masses, they're loud. We don't want bruises on our toes, right? So you'll just stop it as it runs over the rubber band. Okay? And you'll get a graph on your lab quest, is what it's called, from the motion detector. So notice we're not going to do a distance and no stopwatch today. We're using some technology. And so that picture on the left gives you a sample graph. Now, it may look a little different for yours, but you should see that nice increase in speed. Look at the blue or the bottom graph on your sheet. And then it's going to kind of level off, or maybe it'll go ziggity-zaggity as it runs over the rubber band. And so it's that piece that we want data for. Now, I would not recommend eyeballing it. If you select, so you just kind of click and drag with the stylus, then you can do the stat function and turn on stats for the velocity. And the next screen, once you select it, you're going to have some arrows for the velocity graph. You can scroll down to the maximum. So you kind of see that. I don't know if this will let me write back there. Okay, so back on the main screen, you'll be able to get that maximum velocity. If the rubber bands weren't there, it would just continue coasting. Everybody good? And so you'll do that 5 different distances to fill in your final velocity. We're not drawing the velocity graphs that you see on the screen. We're going to draw on page 2. Well, first of all, you got to do the analysis. Use conservation of energy. Gee, didn't we just do that on page 26? You'll use conservation of energy to linearize, figure out what am I going to plot on the y, what am I going to plot on the x, and then on the back side, that's where you'll put your graph, okay? And then later, maybe before next class, you do the slope and figure out what the slope is telling you to get a value for k. And again, if you just calculate k 5 times and take an average, you'll get 0 points for that section, okay? Not best practice. So you'll have a k value, all right? Well, how do we know if that's right or wrong? Well, these rubber bands are not labeled with a k value, and over time it changes, right? And so with our current rubber band in the present tense, we want to use Hooke's law. So Hooke's law deals with the forces. And again, it's not a spring, it's an elastic force, just call it that, so it'll work for the rubber band. It says you're going to solve for k by hanging a known mass, and everybody put in your mass that you're going to hang on it is 200 grams from your rubber band. 200 grams. You'll see a little hanging mass on the side or in the nearby. So here's where you actually need to take the rubber band off the fixed end. So you'll just unloop it. And you probably want to get the match when you take it off. So there's scales around. You don't need the match for part 1. But you bring it to the other end where there's the pulley. And you'll put the string over the pulley. And we're not moving on this one. This is going to be a stationary measurement. And so when you have no motion on the spring, rubber band, fixed spring, well, maybe that that initial position is important, right? Maybe then when I put 200 grams on, what's going to happen? Oh, it stretches it further, okay? And so those two initial and final positions will be helpful in knowing how much it stretches. Make note to self, draw a force diagram. Okay? Force diagram might help on this one. We're not graphing part 2, you're just going to use that data, that one trial, to calculate K. Theoretically, those two Ks for part 1 and part 2 should be the same. And so you'll percent error for those two K values. Good deal? Okay. So I tried to give you some tips there. Hopefully it makes your lab go a little more efficiently, and you know what to collect. I'll be walking around. If you have questions, just let me know. All right? Okay, no more than 4 per group. I think each group actually does have 4, so that's perfect. And so find a station, get going. You have about 30 minutes, and then we're going to finish that page 26 with friction. All right?